Hi, this video is about potential energy in physics. Potential energy is any kind of energy that exists due to an object's position or arrangement relative to other objects. And there are many different kinds of potential energy in physics. There's gravitational potential energy. This exists when you have an object that's relatively high up and it could fall down and do some work as it falls down. Remember, energy is defined as the ability to do work. So if something's really high up, then theoretically it could fall, and as it falls and hits something, it could do work on the thing below. So this is called gravitational potential energy. We also have chemical potential energy, and this kind of potential energy exists whenever molecules are rearranged in such a way that they're ready to release their energy or kind of liberate their energy whenever they're consumed or burned. So an example of this would be food that we eat. The chemicals or molecules that are inside of the food we eat are arranged in such a way that when our body interacts with them, it releases energy for us. The same is true for plants. Whenever they have the sunlight coming in, photosynthesis, it allows them to rearrange molecules, the sunlight does, so that those molecules can be used for other processes like growing and making leaves. So this is all a type of chemical potential energy. Also things like gasoline, things that burn, even like wood after the tree has been cut down, is still chemical potential energy. If it can burn, it has chemical potential energy in it. Another kind is electrical potential energy, and this would be like for lightning as an example. The clouds have a large potential energy whenever they have the ability to discharge this lightning bolt, for example. So electrical potential energy exists whenever extra electric charges are moved to one object and taken away from another oftentimes. So there's an arrangement of electric charges that allows there to be potential energy there. And it always takes work to move charges from one location to another. You can do this by rubbing a balloon against your hair too. You can remove charges from your head, and doing that work gives the balloon some potential energy, and your hair as well. And then another kind of potential energy is called elastic potential energy. And this is any kind of energy when you stretch an object or you compress it out of its normal resting equilibrium. So an example I've drawn here is like a bow and arrow. When you stretch the bow, you give it the ability to do work on an arrow. This could also be like your standard jack-in-the-box or just like a little spring inside your pin. Those are all examples of elastic potential energy. But in order to really understand potential energy, we need a way to measure it. The ones that we're going to focus on in this video are gravitational potential energy and elastic potential energy. Now, to measure how much gravitational potential energy an object has, we have to think about how much work does it take to lift an object up into the air, up against Earth's gravity. So let's say we take this watermelon here. Okay, we want to lift this watermelon up to a certain height, up to here, and let's call this height h. How much potential energy does it gain if we lift it up that high, and the floor, of course, is down here at the bottom? How much potential energy is that? Well, to actually get a measurement of energy, we have to relate it to the work that we do. So the work that we do here is equal to the force times the distance. Now in this case, the distance that we're talking about here is just the height. So I'm going to rewrite this one time to say force times height in this particular case. But how much force does it take to actually lift this watermelon up? Well, the force that you do to lift it up is going to be equal to the gravitational force that's pulling it down. And so that force, the gravitational force, is the mass of the watermelon multiplied by the acceleration due to gravity, which on Earth is 9.81 meters per second squared. Sometimes we round it to 10 to make it a little bit easier to do some math, but that's the force that it's going to take. It's going to be mass times g. So I'm going to rewrite this one more time. The work that we do to lift the watermelon is the weight of the watermelon, mass times g, multiplied by the height that we actually lift it up to. And that's it. That's how much work it takes to lift it. And so by doing work on the watermelon, we give it energy. The higher you raise the watermelon and the heavier the watermelon is, the more energy it will have, the more ability it's going to have to do work as it falls. And so we take this quantity mgh and we call that potential energy. So the gravitational potential energy we represent with the symbols PE, capital P, capital E, and a subscript G is equal to the mass times G times H. So that is the gravitational potential energy. Another common kind of potential energy is elastic potential energy. So a common example of this would be like a jack-in-the-box, where if you were to look inside of a jack-in-the-box, you would see a spring that's in there. And as you crank the jack-in-the-box, you cause that spring to get compressed. So I've tried to draw that here, where the first picture is the spring before getting compressed. We call that the equilibrium of the spring. It's where it naturally would be before any forces are applied to it. And then here is the compressed spring, and it travels a distance here of x, we'll say. So the amount of energy that gets stored up in the spring is going to be related to the work done on that spring. Now the work done on anything is the force times the displacement or the distance. The only problem is the amount of force that it takes to compress the spring actually varies as you compress it. Think about any spring that you've dealt with before. As you stretch it, it's easy at first, but it becomes more and more difficult to stretch it further. So how would we actually determine the work done if we don't know exactly how much force it takes to compress it? Well, fortunately, we do know the amount of force because it's related to a simple law in physics called Hooke's law, which says that the force of a spring is equal to how far you stretch it multiplied by some amount of spring constant. This spring constant tells you basically how springy the spring is. Is it a tough spring or is it pretty loose and easy to stretch? So this is Hooke's law, and if we were to plot that as a line on this graph, it would look something like this, where it's just a straight linear line. F equals kx in this case. So the work done is going to be the force that you apply to the spring multiplied by the distance that the spring travels, which is actually these two axes. So if we multiply these two axes together, we would find the work done. And by multiplying these two axes together of a graph, you're actually just finding the area underneath the curve, or in this case, the area underneath the line here. So if we could find the area here, we would know the amount of work done, and that would tell us the amount of energy that gets stored. So you'll have to remember the area of a triangle is equal to 1/2 times the base times the height. Okay, and so the base in this case is going to be this x quantity here. So instead of base, we'll write x. And the height of this triangle is going to be the kind of the maximum amount of force that you're applying to get this spring stretched or compressed to its fullest length. And so all of that together is going to be equal to the work done. And the amount of work that you do is equal to the amount of energy that gets stored in the object in this case. So keeping it simple, not worrying too much about the differences here, we can say that the work done, rewriting this so that it's a little bit more traditional here, is equal to the force times x. Now we know that the force done on the spring is kx, and so we can rewrite this one more time and say the work done is equal to kx times x. And so finally, we write this one last time. Work equals 1/2 times the spring constant K times x, which just becomes x squared. So this work done is also equal to the amount of potential energy that is stored in the spring. So I'm going to take this equation and I'm going to rewrite it one more time. The potential energy of a spring, or we're going to call this the elastic potential energy, is equal to 1/2 times K, the spring constant, times x squared. So that's where we get our equations for gravitational potential energy and elastic potential energy. Now, you don't have to understand the processes about how we get those equations to understand how we can use them now. So knowing this equation for potential energy due to gravity, it's the weight of an object multiplied by how high up it is. This height is above the zero level. And so the zero level is something that we choose to be, this is the ground level, and anything above this is going to have potential energy. We can choose where this zero level is. It could be at the top of a table, or it could just be the ground, or maybe, it could be, if you're on the second floor, maybe it could just be the floor. It depends on what you need to do. All you need to do is to be able to measure how the potential energy of an object changes. So it doesn't really matter where you pick to be the 0 point, as long as it's useful for you. And typically it's just going to be the ground, or just it'll be obvious where you pick the 0 level to be. Now, for elastic potential energy, we looked at an example of something getting compressed, like a spring getting compressed, but it could also be the other way too. It could be stretched. We always measure the distance away from equilibrium, whether that's to the left or to the right. It doesn't matter either way. So the potential energy from a compressed or stretched object is 1/2 kx squared. Again, k is the spring constant. It's a measure of how springy the spring is, how stiff it is. And then x represents the displacement from equilibrium. So that's all I've got for you in this video. Remember, habit is the battleground of character.